Let's continue with question 4. Now we've designed a lag controller in question 3, and now we will look at the lead controller. Now the lag controller was supposed to change the steady state response. Now here the lead controller will actively change the transients. So we will design a lead controller that affects the transients. Now using the frequency domain, designing a lead controller is pretty straightforward. Let's dive into it. Now, first of all, as usual, we have to define our overshoot value, and then we will calculate the zeta value here. Now, once we've done that, we have to basically calculate the same phase margin here again. Let's get that part too. Now, what's phi m? It's 39 degrees. Now, our transfer function is a bit different this time. We have to update our transfer function. Basically, it's the same transfer function, but there is s plus 2 appended. So let's add the 0 at minus 2 here. So s cubed plus 7s squared plus 6 equals 0. Now, let's begin with the body plot. Let's look at the body plot of the system. Now here we have the body plot. Now we will look at the phase angle of basically the phase margin of the system, and we want to modify that. So the phase margin of the system, plays an important role here. So remember that the phase margin was calculated where our gain was equal to 1. So we need to look at the frequency at which the gain value is equal to 1, and the angle, the argument there, will give us the phase margin that the system has for now. So as usual, we will have the body plot here, and we will search on the body plot. So again, you can go ahead and use the analytical approach where you directly plug in j omega into S and then look for the argument equals 1 equation and then try to solve omega and then work out what the argument at that point is. Now, step 1 is pretty much numerically challenging. So if the system is simple in structure enough, then you can go ahead and do this. If you have a body plot available, why not use it? So let's get rid of the frequency here. We have the body plot here. So what we're searching here is for the gain equals 1. So therefore, instead of looking for the phase, let's look for magnitude and then minus 1. If this absolute error becomes 0, then we would be at that frequency. So let's get rid of this. We have magnitude, phase, and we search for that point. So at a frequency 1.31, the magnitude becomes 107, and the phase value becomes minus 121. Now, of course, we are looking at a value of 1.07. If you want to increase in MATLAB, which is pretty much giving your own frequency range, maybe 1.2 or maybe 1.5. So using this omega, we might increase our accuracy here. But I guess we need to have 2 here. So let's see. Exactly. Now this is practically equal to 1, and our frequency is 1.39. And our phase value, here is minus 122. If you subtract this from, if you subtract minus 180, so phase val plus 180, this gives you 57.48 phase margin. Now our phi m was to have 39. So basically there is a slight difference. Now let's basically get the system's phi, so the phase margin that the system has now, and the phase margin that we want. Now here we have phi max equals phi m minus phi plus 10. So yeah, phi max here is basically the difference between what we want and what the system has in terms of phase margin. And plus 10 is just to be a little bit more safe, in the safe zone here. Now, at this point in the frequency domain methods, what you will do is you will step by step use the algorithm that is to design the lead controller. So we've looked for the system's phase margin. We have a certain phase margin in our mind. The difference between that plus 10 is the maximum phi max difference, basically, that we want to have. Now, let's see what this phi max looks like. It is minus 8.4 degrees. So now, again, we will use a relation here that gives us directly beta, which is basically the alpha of the lead controller. So here we have beta times s times tau times s plus 1 divided by tau times s plus 1. Now instead of having alpha, we have beta here. So we directly calculate this beta by using the following expression: sine of phi max, and then divided by 1 plus sine of phi max. Now, the only problem might be the following, that we are using basically degrees. And here sine of 30 is not 0.5. So is there something like sine d? I guess it is. So keep in mind that when you use a calculator and you have worked out the difference plus 10, in this case, which corresponds to phi max, if you have calculated phi max, you have to be sure that this is in degrees, then you are using sine in degrees. If this is radians, you should then use the correct sign here, or a little conversion may be needed here. So keep that in mind, because that might be one of the errors that you might end up doing. So here we will use sine d for degrees, so therefore our beta should be calculated. So we're pretty much almost there if you think about the in terms of the parameters that we need here. So let's have beta 1.342. This is beta. Now set this aside. Now once we have beta, we will calculate an mmax. So here mmax, which is basically the inverse square root of beta. So once this is calculated, all we need to do is look for the inverse of mmax, or basically we're looking at square root beta. That's also the way to put it. Now we need this gain 1 over mmax, and the frequency where g omega has this gain. Basically we're looking at this gain here. So we have to determine at which frequency this is satisfied. So there's an extra step in searching. So we might go ahead and substitute or look for this 1 over m max here. So let's first calculate it. Let's see. So m max is 0.86 and the inverse is 1.15. So we started with gain equals 1 to determine the phase margin. Now we look at the point where the gain is 1.1585. So let's again take this here and try to come up with a point where this occurs. So instead of using this, I'm going to use 1 over m max here. Now we need only the frequency where this happens. So let's get that. So this is, let's say, omega val 2. So it is 1.25 approximately. At frequency 1.25, this here is satisfied. Basically this one here. So this frequency will help us out in determining tau. So tau is equal to 1 divided by omega times the square root of b, square root of beta. And that's basically it. That's tau. Let's see. Of course, omega val 2. There we go, 0.7. So 0.7 approximately gives us the tau. Remember that we have beta times tau times s plus 1 divided by tau times s plus 1 as the lead controller structure. So we have basically designed it. Now, the design method is pretty much algorithmic. You have just steps to carry out and then you're good to go, which is also the case for the lag controller. But here we have another extra searching step because we look for the phase margin of the system and then the phase margin that we want to have, and then the difference plays an important role in determining a certain gain value, and we look for the frequency where this gain value is satisfied, and that tells us the frequency that the controller should have. And well, when you have beta and tau, you're basically done. You can go ahead and define your controller. So beta times tau and tau 1. So let's try this out. Let's have feedback fs times gs, comma 1. And let's look for the step response and step info, basically. So we have 7% overshoot. We were aiming for 10% overshoot, 30% overshoot. It seems like that our poles and zeros and the method itself gives a certain overshoot. But if you remember when we were talking about the phase margin for the p-type controller, I guess it was question 2. In question 2 for most probably, we were talking about this relation between the phi m and the overshoot. Now there's a slight issue here because we have 1 0 and 3 poles instead of having an all-pole second order transfer function. And other than that, the pole zero map of this closed loop determines also how accurate we are. And since there's a pole zero that looks like this, like this, you can see that we have a 0 that plays an important role here in the response. So if this 0 would not exist, and if the relation here was for a third order system, then we would have better results. So basically the lead controller with a frequency domain has its flaws because we have too many poles and zeros. But by now you should be familiar with the fact that the frequency domain methods do not look at the transfer function model that is available. They have a certain method in designing controllers, but regardless of the structure or model that you have there, you only care about the body plots itself. If you have a certain body plot, you have an approximate, roughly working design methods. It does not guarantee you that you will exactly match the, for example, overshoot, as it is in this case. But the design method is pretty straightforward. The applicability of the methods in frequency domain are for a wide range of systems because you have body plot. You can just take a system into your lab, to your laboratory, and if you have the ability of acquiring the sinusoidal input-output graphics, and if you map it to a body plot, then you're good to go. You don't even have to model it with a differential equation or transfer function at all. Then you can propose a controller that works for the given body plot. But of course, the minor differences or even major differences have to be accepted because your model needs more attention, and just using a body plot can do the best it can do is this. So if you would attack this problem with in the time domain, that would be a more accurate control design for your given requirements. And since we have only overshoot, it is also not really that easy to come up with a, for example, a controller, because you have, again, omega n, which will be in your polynomial equations, coefficient equations, and that may cause some trouble for you solution by hand. So it's also a tricky and difficult question if you think about it. But it has its possibilities because you have this 0 here. Maybe you can choose one pole that cancels this out and then add another 0 that satisfies your requirements here. Now, since we've solved too much of the algebraic method here, what I could do is I could just define k, z, and p as real, and then fss equals k times s plus z divided by s plus p here. And what I can do is I can just go ahead and look for the closed loop as usual, and then take the numerator and denominator num dan of TSS, or even skip it with k times num plus dan as in the previous questions. And then I would have a denominator. Now, since I added a pole, the system is a third order system, I would have fourth order system. And here, the only thing that I know is the zeta value, so I should also define omega n here. And I also need a second order residue polynomial, where I suggest you use just the coefficients here. So s squared plus a times s plus b should be your residue polynomial, because this would a little bit simplify your problem here. Now then you would go ahead and define the desired one. So 2 times omega n times s plus omega n squared. Now the problem would look like this. The coefficients of the denominator and then the coefficients of PDS times PES. Now keep in mind that A and B is real, but the roots may be complex conjugate. The only restriction on PES to have the stable closed loop transfer function is that A and B should be positive. That would be sufficient because this is a second order polynomial. So let's look at the problem here. what is the denominator? So what do we have here? So 1, 2, 3, 4, 5 equations. Oh, comma s, comma all. There we go. Now, let's us also write them a little bit nicer. So the ith element. We can also start from 2 because the first one is trivial. It's 1 equals 1. There we go. Now, as you can see, the problem here is to calculate omega n, because we have omega n squared all over the place. And the only thing that we know here is that a should be positive. We have p, which should be hopefully positive, not mandatory, but would be a stable controller if p is positive. And yeah, what do we have? We have a, b, omega n, k, z, and p, which makes 6 unknowns, but we have only 4 equations. Of course, it is also possible to omit this k, because z divided by p, as I've told you in the leg controller video, you can define s plus z divided by s plus p, because z divided by p will work as k. So then we are reduced down to this one here, where k is not there. So z, p, omega n, a, and b makes 5, and then we have 4 of them. So this is basically, again, an optimization problem, because we don't know what omega n should be. Now the question would be, how can I get at least a stable set of controllers? Well, in this case, just having a and b positive would correspond to stability. But as you can see, not knowing omega n is the big struggle here. If we had, for example, omega n equals 1, then this would be a plus 2, then p plus 7, 7p plus 12 would be 1 plus 2a plus b, so linear. And then this will also be linear because omega n is known, and this one would also be linear. So you could just choose any one. So you might go ahead and define omega n instead of this. Just say omega n should be equal to 1, for example. If nothing else is given, this is the only way. So then we would be reduced to this one here. So a plus 2 to a plus b plus 1, a plus 2b is the right hand side. Then we have 12z, 6p plus 6z plus 12, 7p plus 12, and p plus 7. So p, z, a, b. We have to solve them. Of course, here it's also a little bit of a challenge, but instead of b, you can plug in 12z, which should get rid of this part here. You have to work your way up. So basically, getting rid of zp would be the choice, or ab. So you get one side of the solution and require all of them, all of the parameters or unknowns. So let's solve the problem here and see what the solution is. Solve that a is 36 divided by 5. Solve that b. I'm checking if they are positive. They are. So I could use solve that p and solve dot z here, which seems like a good controller choice for now. I don't know what the dominance factor here is, because in this case we are trying to design a lead controller, but we should utilize the dominant pole assignment method here. So 2 of the poles should be in the dominant region, and all the other poles and zeros should be pushed away from them as far as they can be pushed. So let's have, let me look for z-val, which should be double sol dot z, and let me repeat it for p. Z-val and p-val. Once I have the controller defined, I can go ahead and copy paste this part here and see what happens. Maybe fs2 in order to be able to compare. So we can see that we don't have any overshoot because, again, we need to check what the pole zero map looks like, what the pole spread is. So we have to have the dominance, dominance factor here. Let's get rid of this. Let's get rid of these. Copy this and look what the pole zero map looks like. So there we go. Now it's similar cases here. As you can see, we have a 0 here, and then there's a 0 pole cancellation, which seems like has an effect still because they are just near. So maybe choosing a different omega n value, maybe increasing it a little bit, could solve this issue, but seems like it's getting worse. Let's try something else out. Seems like, oh, this one is not even close to what we want. So let's stick with equals 1. Now, of course, it is possible to try to solve this in terms of a parameter. Now, if we have, for example, in terms of omega n, then we would proceed in examining the zeros and the characteristic polynomial. So let me quickly show you what I mean by that. So let's say we are solving, and this will be a little bit tricky, but let's try. Let's try to solve A, B, Z, and P. So there are 4 equations, and we want to have P, Z, A, and B as functions of omega n. So in that case, hopefully MATLAB can help us out. Seems like it does. So yeah, it has one parametric solution. Now at this point, we know that A and B will be changing with omega n. So they are basically functions of omega n. There we go. Of course, these look very ugly in terms of complexity, but it is what it is. So what we can do is we can do the following. We know that the PES, so the residue polynomial, is s squared plus as plus b. So, and the other one, the dominant pole should be this. So how can I determine what, for example, the sum here is? If they are complex conjugate, then I would be it would be sufficient to look at A, because then I can assume that the real parts are this and they should be further away. But of course it's not really that easy here, and since our parameter is also not linear, we are in trouble here. But since we are using here MATLAB, I might demonstrate you something. We could do something like this. Let's have omega n vec, and let's try the values of by the way, let me look for something. So solid A has this here and this here. Well, it's hard to say something about this, so let's try something. So let's define omega n vec over an interval 0.0, let's say 0.1 up to 2. So Here what we can do is we can calculate the A values. So instead of having sol.a, instead of omega n, we want to have omega n vec. So there we go, we have A values, and we can repeat this for B. So A vec, B vec. Now we can see, for example, that at this point, these values are not valid, because here we have negative ones. So starting from this point up to here, we can see that we have positive B. And also this one here is negative, so we can't use that one. But since both of them should be positive simultaneously, I have a certain lower limit. So let's try to match that by trying 0.5, I guess. A vec and B vec. We should still increase 0.1, which means that 0.6 is a good estimate here. A vec and B vec. Now at this point I can see that starting from 0.6 omega n, I have stable solutions. At least stability is achieved at this point. And choosing, for example, omega n 6, 0.6 here, should give me a result. Now we can go on with Z and P here. Now let's have Z vec and P vec. Instead of this, let's have Z, let's have this, let's have P. So we have Z vec, and then P vec, and there we go. Now these are the controller poles and zeros, basically. And what we should do is we should look for the roots of basically 1 A vec and B vec. Of course, we have to do this in a for loop. For I equals 1 to length omega n vec, we have these roots. So here we can see that we have minus 18 and 6. So the closest one is minus 6. And then at minus 5, minus 4, minus 3, minus 4, 2, 4, 1. So basically, these are not very useful for me. The best solution seems to be somewhere here. Now, these are also not good. So the first value of omega n vec is basically the best I can do in terms of the residue poles. So let's stick with omega n val equals 0.6 here. So this seems to be a reasonable solution. So let's basically what we do is we say index 1 is the best one. So A val should be A vec index, and repeat this for the other ones. So B vec, Z val, Z vec, P val, P vec. So hopefully, if I use, where is it? Oh, we got rid of it. Okay. Fs equals Tf. If we use one Z val and one P val, I don't know what the zeros are. I didn't look at the zeros because the system has 1 0 and I'm adding another one. So I should be looking at Z vec here, basically, to determine it, and it will be at 3.37. So even though I can push the poles to minus 6, I cannot push the 0 further than 3.3. So hope that this works, but we'll see. So let's have the closed loop, fs times gs comma 1, and then figure one step TS, step info, TS, and then figure 2, PC map. Now we still don't have any overshoot, which seems like the basic issue here. But you can see that we have one pole here, interestingly. Now, what is ZBK? Okay. Now, didn't we use zeta? We didn't use zeta. Okay, that was our main issue. Yeah. We have to look at it once more. So now we're talking. Yeah. We unfortunately forgot to include this zeta, so we were looking for zeta equals 1 for solutions. Therefore, let's get rid of this and try to look at AVAC. Seems okay. BVAC. Yeah. It seems like 1, 2, 3, 4, 5. So the 6th element here should be our value. So I guess something like this should work. So what's AVAC? It's positive. What's BVAC? It's also positive. Now at this point I can see that A increases and B increases. So let's look at the roots. Minus 0.5. So yeah, I should increase a little bit more, seems like the case. For example, is it better to increase? Now we're stuck at -2 here. Even though I increase it, it seems like that it starts to decrease here somewhere. So 252, 53, 5, 7. So this is basically max. So I should choose that value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 19th solution or 20th solution should be good. So 3.2 seems to be a good candidate. So this is the first one. So yeah, it seems like we cannot get rid of the effect here. So let's try it once more. Now the problem is that this problem does not specify any settling time. So therefore it's really tough to have the best setup here, because not knowing the settling time makes the problem harder. So yeah, at this point we can see that we have a complex conjugate pole pair here, a almost cancellation here, and one pole and 1, 0 further away. And it is almost ideal because we have 38.57% percent overshoot, and we were aiming for 30%. So this is way better than the result of the frequency domain methods. But keep in mind that we just used gridding here for omega n, which is not likely a problem that you should encounter because the solution of omega n is very, very problematic. But what if we had the settling time specified or something related to omega n? So let's say we know what omega n is. At that point, the problem becomes much easier because it is linear now, and you can work your way out. So that is more probable. So keep that in mind. And once you have it, you can go ahead and solve it just for the one parameter. And what you can do is you can determine what the closed loop will be, because our issue was to get a linear equation set and to isolate one variable. If you isolate one variable, you can just plug it into PDS or even PCS or PES and look for the root locus of this here. And you can repeat the same for PZS, which would be basically this one here for this controller. But if you have, for example, a PID controller, that should be what you should try. You should try to look for PES, the root locus of this, and the root locus of the zero polynomial. In this case, we have also, of course, S+2. So that basically concludes our question for this. You can see that we have used the same phase margin for the frequency domain methods for 30% overshoot, but the system itself had a different phase margin, namely 57.51. So we needed to decrease it. Therefore, we used phi max, which is the maximum difference between the phase margins. And then there is this relation 1 minus sine of phi max divided by 1 plus sine of phi max. So we get beta. So acquiring beta is quite easy. But we have to work out what the gain would be and where this gain plot satisfies this at which frequency. And that frequency helped us in determining the tau value. And that's basically it. Then you have your controller. Now this was too easy to be true. So we looked at the response and it was okay in some terms. And you can see that this is a lead controller because it has positive phase. So the B1 was basically not even solved in my PDF because it doesn't really relate to the problem here, but you can go ahead and try to solve it. The best you can do is 38.57 if you have a little bit of an eye for it. I basically eyeballed it here, but what I should do, I should use the tabulation method, try each point with a higher accuracy, a higher grading, and then get the results. But it's not really likely here that this is a pen and paper question. Now, if you have a pen and paper question, the only difference would be that you would be able to isolate one parameter for each parameter that you have here. And you would use that parameter, since you have only one parameter, you can look for all polynomials, the zero polynomial, the residue polynomial, and you can get a feel for their movement because you can use root locus for them. And since they are not high-level polynomials, it becomes quite easy. So what you have to do is you have to check the root locus corresponding to PES and to the zero polynomial. And that's basically it.